The story of Hamlet protein starts more than 30 years ago in the rural parts of Denmark. Today, we are a multinational company specialized in young animal nutrition. We believe that the well-being of farm animals starts with health, and that healthy young animals result in healthy business for all stakeholders. We produce specialty soy ingredients for young farm animals. Young animals cannot digest soy as it contains anti-nutritional factors. Through our patented bioconversion process, we minimize these ANFS and produce products that the immature gut of young piglets, calves, chicks, and fish can absorb. At the same time, we leave the essential amino acids of the soy intact. Our fully automated production process ensures that our customers around the world receive the same high-quality product, whether it is produced in Findlay, Ohio, or Horsens, Denmark. Hamlet Protein is committed to the environment. We constantly strive to reduce our ecological footprint by optimizing the use of natural resources. For example, excess heat from our production facility in Denmark is redistributed as heating for more than 3,000 households. So whether you are a feed mill, premixer, integrator, or farmer, you can rely on us as your responsible and transparent partner when sourcing protein for efficient young animal nutrition. A healthy business starts with healthy animals.
Ladies and gentlemen, welcome back to the Livestock Management webinar. I hope all of you had a good lunch today. My name is Jomia and I will be your moderator this afternoon. Before we start, I am going to walk you through some helpful tips so that you can maximize your benefits at our webinar. For some sessions that are supported with Vietnamese and English translation, please use the interpretation function found below your screen. Click into the Vietnamese or English to choose the language you wish to listen to. To raise questions to our speakers, please type your questions into our Q&A box found below your screen. And after this webinar, if you want to obtain the certificate, please make sure you complete our survey form and send your request to us. So without further ado, I would like to call on our first speaker for the afternoon session. Mr. Lars Andersen is a nutritionist from Hamlet Protein. We'll be discussing the difference of different specialty soy proteins. Hamlet Protein promotes the health, welfare, and performance of farm livestock through soy-based specialty proteins for young animal feed. Around the world, our products are known to deliver an efficient, high-quality source of vegetable protein with a strong return on investment. So now, I'm giving the floor to Mr. Lars Andersen. Good afternoon, sir, and thank you for being here.
Thank you very much for the introduction, and thanks for organizing this Livestock Management Day and inviting us to participate. And I'd also like to thank the attendants for joining and listening to what we have to say today. I hope you also, as the moderator said, had a good lunch and are ready for a little bit more information this afternoon. I would like to talk to you about the specialty soy proteins that are produced and used widely today in animal nutrition. The issue is at hand that depending on the processing method used for producing a special soy protein, the quality of that particular product can vary compared to other products. So it makes it hard to compare different soy proteins unless you are aware of which differences can actually occur. Also, knowing the process behind the actual product can be valuable in evaluating whether this or another product should be the one of choice in your particular feed. So what I will talk about is, first of all, soy as a raw material. You can hear a lot in different parts of the world regarding use of soy. In Europe, there is an anti-soy movement considering import of soy from South America, which is also largely what comes to Asia, including, of course, also soy from the US, but especially the soy from Brazil is being criticized for costing a lot of rainforest to be cut down, and therefore there is a criticism of this soy. So I'll just talk a little bit about why it is that we're actually using soy in so many cases, and then about the processing and why we do the processing. So talking about the anti-nutrients that are present in the soybean. And then mention the effects of the processing on the quality of the final ingredient, the final product. That leads to talking a little bit about digestibility and ingredient quality, how it is affected by processing, and what that means for the use of the product in the formulation. Having established the knowledge on the anti-nutrients levels in different products by analysis in your particular case, you can actually use those anti-nutrients in your feed formulation. We may not know all the minimum or maximum values that are acceptable in feed for different animals, but by making a calculation on the level of anti-nutrients in different diets, you get a very good picture on what works in your situation and under your conditions with the ingredients that you have available, and which level is too high. So that is one way to use these anti-nutrients. And then, yeah, of course, just a take-home short conclusion to round it off. Soy has sometimes been called a blessing in disguise. The blessing comes with the fact that it's a very cost-efficient protein source. We have an abundant supply, as I will show in a second, and soy has a very favorable amino acid profile, which I'm sure a lot of nutritionists are very well aware of. The amino acid profile of soy fits quite well monogastric animals, with a few exceptions that has to be added, of course, but that is also why we do the feed formulation. But also from nature's side, soy has a number of anti-nutritional factors inherent in the bean, something that the bean produces as a response to the environment that it grows in. These anti-nutrients can decrease the use of the product and the usefulness in different animal feeds. And typically, the younger the animal is, the more important these anti-nutrients are, for two reasons. One is that they are not fully developed in the digestive system, and therefore are not able to overcome the effect of the anti-nutrients as easy. The other thing is that the animals having the highest protein requirement, and therefore often being offered the highest soy inclusion in the diet, are the young animals. Chicks, piglets, calves, they all need more protein compared to energy in the feeds that they receive, because their muscle buildup and internal organ buildup requires a lot of amino acid, a lot of protein. Where older animals need more energy for maintenance and the fat growth that comes later in the animal development. Mentioning that soy is in abundant supply, I would say here that I calculated yesterday the production of soy worldwide in 21-22 so far. Adding the most important countries, we arrive at more than 350 million metric ton of soy produced in the world. And that is actually more than all other oilseeds put together. This brings an aspect to the discussion whether we should use soy, as we have in some countries at least. The problem here is then that if we don't use soy, what are we then going to use? Because there isn't an available alternative, at least not right now. So a lot of good efforts are made to introduce supplements to soy, like insect protein, bacterial protein, and all these attempts and productions are very good, but it is going to take a very long time before they can replace the 350 million metric ton of soybeans worldwide. So until now, we are still going to have to consider using some soy products, and therefore we might as well also look into why we use certain soy products preferable to other soy products. If we look at piglets, we know that we have what we call weaning stress. It has been described so many times, so I don't need to go into details with it. The truth is that weaning stress is a lot of things. It's a change of diet. It's exposure to these antigens that we find in several ingredients in the feed. It is also exposure to pathogens in the environment. It's social stress from being mixed with other animals from other litters, and typically also an environmental change that occurs at the weaning time. If we then look past the weaning stress inside the animal and see what is actually going on, we will see that there can be some inflammation. A big change is going on in gut microflora, and there has been some very good webinars this winter on development of microflora and what can be done. So this is a very important area to stabilize growth in the future for the animal. There is oxidative stress going on, which can harm the gut long term, and a change of the gut surface, which can come from different sources of input from the feed, typically, that can affect the intestinal barrier dysfunction, so that the protection against microbes from the environment breaks down, and we see reduced immunity, reduced ability to fight diseases like PD or PRS, and therefore an increased mortality. And I like this slide very much because it sort of indicates that it's not a straight line, that we have something happening and it gives weaning stress and it's caused by one thing. This is multifactorial, and if we can improve one or more of the impacts on the animal itself, that means we can help reduce weaning stress, and that means that we may have an effect on all the things going on inside the animal, and therefore the performance results that we get. What has typically been done to reduce this weaning stress problem is to add either zinc oxide and or antibiotics to the feed. And just showing here the use of antibiotics in different countries in the world. You can see that there's a huge difference. I'm not pointing fingers at anyone, just showing that the use of antibiotics are very different from region to region. But that also tells you that if you look at the people using less antibiotics, there may be something to some knowledge to acquire that can be used to reduce the use of antibiotics. Today, as you probably know, in the EU region and certain countries in Asia, I know, have followed the EU on this decision, reduce the use of pharmaceutical levels of zinc oxide to maximum 150 ppm, where it was standard to use 2 to 2,500 ppm zinc oxide in the feed. This happens in June this year, and after 26th of June, there will be no allowed levels of zinc over 150 ppm. This we have to figure out how to work with and how to feed the animals according to those new regulations. Therefore, it's important to go and look at the ingredients that we put in the feed, if we can improve on that. Here is an overview of the different steps in soy processing, starting with the raw soybean and then having the hull, the shell removed, and typically some kind of heat treatment to what is known as full-fat soybean meal. Then the standard high-pro soybean meal, and I know that also comes in a low protein where the hulls have been put back. Then some companies extrude the soybean meal to give it further heat treatment. Others use fermentation to improve the soybean meal ingredient. In Hamlet protein, we use an enzyme treatment. And then there are different ways of producing soy concentrates, either with water and reduced pH, or with water and alcohol. And that depends on the starting raw material for the concentrate production. If it is a soybean meal, then you typically get a lower protein content in the concentrate, products like Selecta, for instance. If you use what we call white flakes before they're being toasted, then you will see a higher crude protein content, like, for instance, in soy meal. And then finally, we see soy isolates that are produced in a different way, but are used mostly in human food, sports drinks, and so on. So they're usually also very expensive products. The content of these anti-nutrients that cause problems for the animals, they are highest the lower the processing level is. So in a raw soybean, it will be very high, of course, and in a full-fat soybean, which has had typically an extrusion, there will still be a relatively high level of most of these anti-nutrients. There are trypsin inhibitors blocking the protease in the gut, reducing protein digestibility. There are antigenic proteins causing damage to the gut wall. There are sugars, oligosaccharides, causing damage to, causing growth of pathogenic bacteria typically. Lectins, if present, cause damage to the gut wall. And phytic acid, of course, decreases digestibility, especially of phosphorus, but also other minerals and amino acids. In the soybean meal compared to the full-fat soy, you can see there is a reduction, but it's definitely not complete. And there are still relatively high levels of some of these anti-nutrients present in the soybean meal. Therefore, if we want to use it for young animals, we should consider doing something more than just the simple toasting that is the process for soybean meal. If we range the products a little bit, then I have the category that I would call ordinary soy products. They include the soybeans, of course, but I don't think anyone uses raw soybeans. They include full-fat soy that can be processed, as we will talk about later, in different ways. Soybean meal, which is more a standardized product, either high pro or low pro, but I believe that for most animals today, we use a high pro soybean meal. And finally, that belongs also to the ordinary products, extruded soybean meal, because the only thing that has undergone processing here is a heat treatment through the extruder, and that doesn't really change the property of the product a lot. If we then look at the what I would call more processed soy products, refined soy proteins, then we can start with the fermented soybean meal. That is a very old process, originated in Asia thousands of years ago for human food. And I would say, especially the last 20 years, it has become a very common process for also animal feed. Before 2000, we didn't see a lot of fermented soy products in Asia either. Enzymatically treated soybean meal is not only but mostly HP 300 or similar products from Hamlet protein that are, I think today worldwide known. We have sales in 60, 70 different countries. And we have been producing this since 1993. Then we have the soy concentrate that I mentioned, based on soybean meal that has been toasted. And we have the soy concentrate based on white flakes or on the water extraction with the reduced pH. And then finally, the soy protein isolates. If we look at the raw soybeans, of course, that's a no-process product. They are extremely high in anti-nutrients, and they will have a very poor standardized ileal digestibility. Way below 50% of the protein will be used by animals if we give them raw soya, which I don't believe anyone would consider anyway. The extruded full-fat soy is a very common product today, and probably the most common product, because putting up an extruder is a more simple process than some of the other, and also more efficient maybe than some of the other. But full-fat soy can also be micronized, so ground into very, very fine particles, also under heat treatment. It can simply be toasted, which is not a very good process, or it can be jet exploded, which is probably easiest explained by comparing to popcorn, that you maybe with a microwave energy source and some moisture present can make the inside of the bean turn out. Or it can actually be pressure cooked in some water. That is probably the most not the most used process, but the most careful process to preserve the quality of the protein. The problem with full-fat soy is that when you want to heat treat a product to reduce the anti-nutrients, and that product also contains 20% of oil, you will have a high risk of damaging the oil quality by oxidizing the oil. When you expose it to a lot of heat under atmospheric pressure with oxygen present, there's a risk that the oil starts oxidizing. And if you do add a lot of heat, you will cause a huge fire, because the oil will catch on and start burning. But also the oil protects sort of the anti-nutrients against too much heat, because if you extrude a product with 20% oil, there's a limit to how much pressure you can actually put on before it slips through, greased by the oil content. Soybean meal, a well-known product. It's extracted for oil by hexane, and once the hexane has been evaporated, then the beans are toasted, typically at 130 degrees for 15 minutes, and then the product can be micronized or ground into very, very fine flour. That increases digestibility a little bit by reducing the particle size and increasing the surface area, but it still contains most of the anti-nutrients that were present in the normal soybean meal. Extruded soybean meal, as I mentioned, It's again, of course, hexane extracted and toasted. And then after that, it's put through an extruder. Originally, when the type of product came out, it was a little bit puzzling why it should be extruded, because it has already been toasted, and the extrusion is not much more than a second heat treatment. The thing is with the extruder that for full-fat soy, it helps open up the oil cells, so it makes the oil more available. If you extrude cereals, then you can open up the starch molecules for better digestion. But in soybean meal, there's no oil left and there's no starch. There are some of these sugars and oligosaccharides that are not affected by heat. There's protein and there are fibers, but no starch. And the fibers are not affected by the heat. So it's merely to reduce the antinutrients, and they will only have a certain effect on those. They risk, on the other side, to increase the heat damage done to the protein by a second extrusion over the toasting. Then the fermented soybean meals are, of course, first of all, hexane extracted to take the oil out and toast it as normal soybean meal, and then subsequently used for fermentation with one or more microbes. That can be bacteria like bacillus, lactobacillus, and others. It can be aspergillus, fungus, in at least one product that we know. And after the fermentation, the product is then toasted or heat treated and dried. What we see is typically that the process takes 2 to 4 days in a dry fermentation method, where the product is mixed with some moisture and the inoculate, and then it's put in a pile on the floor and left for 2 to 4 days before being toasted and dried. That has two effects. One is the batch-wise production. That can mean that the quality can change from one batch to another. And the other thing is that the subsequent toasting in the toasting / drying can also heat damage the protein if it is not done in a careful way. In HP 300 and our other products, what we do is that we also use the extracted toasted soybean meal. We put it through an enzyme treatment, and that is a continuous process where the product can be monitored and quality can be controlled throughout the process. The process can be changed using different enzymes, and we can have different product qualities coming out of it. Then, of course, it's dried and milled. The drying is using air and steam, not plate or drum dryer. And temperature is kept to a relatively low level so that heat damage is avoided. And this is easy to say, but when we look at digestibility trials, that also is shown that it is one of the most digestible products of the soya products that comes out of these processes. And finally, of course, it's milled and bagged for use. Concentrates based on soybean meal. There you have to look into each product to find out whether they are used on produced on soybean or what we call white flakes. But if they're based on soybean meal, they are typically not high in protein, which means 60–62% protein. Again, hexane extracted with to remove the oil and toasted, and then later water alcohol extracted, and then finally toasted again. And that toasting might not be necessary, but it's a standard to do it, and that's what's happening. So like the fermented products, we sometimes see products that are soya concentrates, but are not having a very high digestibility due to this double toasting and heat damage to the protein. The soy concentrate based on the white flakes, they are processed in the same plant or a neighbor plant to where the hexane oil extraction occurs, and then the product goes directly from there and into the water ethanol extraction. So there's no in-between heat treatment or storage of the product. It goes straight from one process to the other, and that means that it's possible to remove more of the carbohydrates. Apparently there's, in the heat treatment, if it's toasted, there's some matrix formed between the protein and the carbohydrates, making it harder to extract the carbohydrates and up concentrate the protein. But in these products using white flakes, we see 65 to 68% protein in the product, not dry matter, but in as is. So there's a clear increase in carbohydrate removal from these products. And again, of course, once the ethanol is evaporated from the soy concentrate, then it is toasted to reduce trypsin inhibitors and to reduce the antigenic protein. And those products like soy meal coming out of this is probably a really good quality when it comes to that. If it's water extracted, and that is actually a very old method, but a company here in Denmark have started producing this again recently. Originally, when soy protein concentrates were invented, it was just with a water extraction. But if you mix soybean meal with water, you will also solubilize a lot of the protein, and that means reducing the protein content of the final concentrate, and that is not what we set out to do. That's against the goal. So in order to avoid the protein being soluble in the water, pH is adjusted using, in this case, citric and sulfuric acid. When the pH is down to a low level, the protein is not soluble, and then you can solubilize the carbohydrates and then remove them with the liquid phase, and you have a soy concentrate left. That is then homogenized, filtrated, and again pH is then adjusted to 4.5 to 5 using sodium hydroxide, and then dried and toasted. So it's a much more complex process. It's using different chemicals and resulting in a different quality of the final protein in the product. Just mentioning, mentioning shortly the production of isolated soy protein. The way of producing isolates is to put the soybean meal in a very high pH solution that dissolves the protein, and a lot of the carbohydrates and other components, they will stay at the bottom as a precipitate, and then you remove the liquid phase, including all the protein or most of the protein, and you take that liquid and you put in some acid to drop the pH to a very low level. That makes the protein insoluble, and then the protein will precipitate, and you can remove that. If you then repeat the process 1 or 2 or 3 times, you get a very, very clean product. You can get even higher than 90%, and with a very high solubility. Again, that is a very expensive process and is often used for sports drinks and stuff like that, so not available easily for feed production. Just illustrating the problem with this 2 times heat treatment of products today. Most soybean meal producers, they are trying to make a good quality product to get paid a decent price for it. They know if they don't do a good heat treatment, people will not like the product. So they try to hit this optimum. When you increase heat treatment temperature and time, you increase the digestibility of the protein until you reach a level where you have decreased the anti-nutrients to a low level, and you start damaging the protein by increasing heat treatment, because then the digestibility starts falling again. Probably not so fast, but it falls nonetheless. The trick is, if you want to increase soybean meal, you have to find a way to move from here and up. Apparently, we have found a drying method used in Hamlet that has some of that effect. But if you use a normal toasting, there's a risk, at least, that you can move down this line and you end up having a lower digestibility than your raw material did. Finally, then looking at the anti-nutrients in the soybean refined processed products. We had the full fat and the soybean before, looking at enzyme treated soybean meal, so HP 300 from Hamlet protein. You see an increase in protein, and that does not only come from a reduction in moisture, but from a removal of these sugars here. They are removed by 90 or more than 90%. You see a almost complete elimination of lectins and reduction in phytic acid, and practically antigen-free product, 2 parts per million. So it's barely measurable at all. Trypsin inhibitor is also quite low. Zero doesn't exist for trypsin inhibitors, because if you get to 0, or I would say if you get to less than 1, you have heat damaged the product. The last little bit of trypsin inhibitors are very, very difficult to get rid of. And products with a very low trypsin inhibitor content can be heat damaged, and you have to be aware of that. The fermented soybean meals are not a homogeneous product group, depending on processing and bacteria and the method used. There's a relatively huge variation from quite okay quality products, quite good products, and to products that are not much better than soybean meal. So it's very important to make sure what kind of fermented soybean meal is being looked at when you consider including it in animal feed. The soya concentrates, here I have put in the ones produced on soybean meal, because they are the largest part of the soya concentrate being produced. And they have a certain removal of anti-nutrients like trypsin, not a complete removal of beta-condyl, probably because the carbohydrate protein matrix protects the proteins from being attacked by the alcohol, and therefore not denaturing it. If you compare to soy committal, the quality here is similar to Hamlet, 1 to 2 ppm. Also, the sugars are not completely removed, again, probably due to this matrix formation, and there's no effect on phytic acid. What all this then results in is hopefully that the animal are better able to digest the proteins left. a very large study at University of Illinois, done by a lady from Brazil, Juliana Ranches, showed that when she looked at all the trials worldwide that were to be found on pigs using soybean meal in the diet, that came out, I didn't put the level here, but it came out at around 85, I think, %. And that wasn't different to the low protein, the 44 or 43 soybean meal. So you could say for pigs in general, there's not a huge difference between these two groups of soybean meals. Hamlet protein enzyme treated soybean meal came out at around 90% in digestibility, and the fermented soybean meals came out at, I think, 81 or 82. And this is probably due to the fact I mentioned that the heat damage is too high in at least some of these products. So I concentrate not much, but slightly lower than Hamlet, and isolate actually not that high, probably because they're used in human foods and people do not really worry about the heat treatment, since we are not on a minimum protein diet every day like the pigs or the chickens are. We probably get more protein than we need anyway, and therefore, because there's a bit of trypsin inhibitors, that doesn't really matter so much. But this was for pigs in general, and we are talking young animals typically when we talk processed soya. So how does it look if you look at the young animals? And then the difference becomes much more apparent. When the pigs are less than 20 kilos, digestibility of soybean meal is lower. Hamlet protein and the soy concentrates are definitely at a much better level. And fermented soybean meal, again, is similar to soybean meal. So at least the digestibility wasn't decreased like I indicated it could be, but it has also not been improved. So the removal of anti-nutrients and the heat damage have equaled out, and we haven't really stepped a lot forward here. Yeah, I mentioned the SPCs. They are in digestibility relatively close to Hamlet protein. Soy isolate also, again, not significantly different, but numerically a bit lower than the feed products. Probably, again, people do not worry about this as they're used in sports drinks. Then you might question yourself why I worry about digestibility, because that could be considered just to be a calculation figure used for making sure you put enough amino acids in the diet. But actually, if you compare over a lot of trials, you can make a calculation relating feed intake to digestibility of the feed. And the very low digestibilities are definitely not relevant for the feed that we give, especially young animals. And these very high digestibilities are probably not achievable or economical to use in animals. But even if we focus on the middle third of this curve, we can perhaps increase feed intake by 25 to 50% by focusing on increasing digestibility of the ingredients that we put in the feed. So therefore, it is important to make sure that the protein, but not only, also the cereals, have a good digestibility when they are fed to young animals. I mentioned that it could be a good idea to use this knowledge on anti-nutrients in your feed formulation. Here I just put in the nutrient overview from a feed formulation we do also in Hamlet. where we then have added to the nutrient list stachyose as a representative of the sugars, trypsin inhibitors, and the beta-con, the antigenic protein. And then for the for the protein ingredients, typically the soy products, we then analyze and enter into our table the amount of antinutrients, and then we can see as a consequence, when we have made our feed formulation, what are the consequence in the stachyose, trypsin, and beta-conglycinine content. And maybe one day we have a figure that we can say, okay, it should be maximum so much. Today we just keep an eye on it and say, okay, this diet we know works very well, so this is probably a good level to not exceed. We are working on trying to establish recommended levels of these antinutrients in feed formulation. The problem, when we talk pigs at least, we have recommendations for poultry, but we're talking pigs, it means that it probably depends a lot on the size of the animal and the amount of other ingredients that are in the diet. And therefore, it's not easy to put a figure on here. So I hope that you can agree and have the same impression of the data that we have looked at to conclude that using ordinary soy products can be very challenging for piglet health and all the other young animals, of course. When you do processing to soy to improve the anti-nutrient level and the digestibility, this processing affects the quality of the finished product that you are making. And it's very important to evaluate the process and the resulting quality of the product before start using it, to make sure that you actually achieve what you set out to do with the improvement in the diet. But that it is actually possible to achieve high quality soy protein products useful for young animal nutrition, so at least equal to animal proteins, probably sometimes also better. So that should be my finishing words. Thank you very much for listening, and if there are questions, then I'll be happy to answer.
Okay, and that's the presentation of Mr. Andersen. Thank you so much for enlightening us about the production soybean worldwide. And we are so enlightened with the different causes and consequences of breeding stress. And this must be well addressed. So now comes to our Q&A session. If you have any questions for him, please feel free to type in your questions into the Q&A box found below your screen. So I'm going to read some of the questions from our audience. So first question, Mr. Lars, can you explain a bit more about the biotechnological process?
Yes, the only thing I cannot say is exactly which enzymes are used, because that is a proprietary part of the process. But I can mention that what we do is that we mix soybean meal with moisture, and we add our enzymes into a continuous flow process where the product is moved along for several hours, typically half a day. It's a faster process than the fermentation because of the movement of the product. And it's a controlled process because we can take out samples along the continuous flow system and monitor how well is the process running. And that also ensures more consistent end product quality. Once the enzymatic treatment is done, then the product will go into, let's say, sterilization, where the effect of the activity of the enzymes is stopped. When adding enzymes to a feed ingredient, if you do not remove them then you have to specify on the back which enzymes are added. And after the process, we wouldn't be able to say how many enzymes are left in the product. So this sterilization is just to make sure there's not any more activity. And then again, the drying is done with air and steam to avoid having a very warm surface that touches the product and could damage the protein quality.
Okay, and this is another question from the same person who asked the first questions. The question is, what are the differences in your products? For example, the HP 300 and the HP 200.
Yeah, the difference between 2 and 300, they are mainly that markets asks for cheaper products sometimes, possibly for also using in larger animals, so not the very young ones. And as a response, we have made HP 200, which is processed in shorter time and therefore has a lower protein content and a little higher level of anti-nutritional factors. But due to the fact that we then can produce more product per hour, makes it a cheaper choice. So it depends a little on what it's going to be used for. If it is very small animals, 6 kilo weaning pigs, I would not recommend it. But if they are 12 kilos and upwards, then it probably is a good choice.
All right. So let's go to our third question from our audience. So the question is, why CP digestibility of FSMB is lower than the others?
Yeah, I don't have the full question, or the full answer for that, but I believe, like the author of the publication, Juliana Branches, that it is a possible heat damage done to the product. Of course, I don't know all fermented products. There are many producers of fermented products in Asia, especially. But I do know for some of them that the typical way of drying the product after the fermentation is finished is on a drum or a plate dryer. And if you imagine a drum dryer, it's maybe a rough way to say, but it's a little bit like a frying pan. You put a thin layer of product on it, but even a thin layer of product, some particles will touch the hot surface and probably become heat damaged. Other products are on the outer layer of the particles, and they may not get enough heat treatment. So in the final product, you have a product that can be partly heat damaged and partly not properly treated. And I believe that's what's occurring. If you compare to soy concentrate like soy meal or Hamlet protein, they use air and steam drying. And there you have particles suspended in an airflow, giving more or less the same heat treatment, all of them, and none being undertreated and none being heat damaged. So that's possibly the difference.
All right. So here's another question, and personally, I also want to know about this. Will the pigs perform if there are no animal proteins in the diet?
Yes, this is a question we have discussed a lot, especially since 2000, where in Europe we had the BSE crisis, and animal proteins were banned, including fish meal in some instances. There was a big concern that the animals wouldn't eat and wouldn't grow properly. Today we know that it is not the case. It's absolutely possible to make a diet based on vegetable proteins that can make the animal grow and also make it want to eat the feed. So sometimes bad things happening like BSE or PED learns us that we can do things that we didn't believe we could do before.
All right. So here's another one from Liani. What kinds of laboratory tests can show the quality of SBM other than crude protein? The
most simple other analysis, if we talk soybean meal, is urease, where that's a very, very simple test that can be looked up on the net or asked from a lab. You can buy a small kit that you put in a small amount of soybean meal, and after a few minutes, you know how much urease activity is in the product.
Mm-hmm.
The urease is an indicator of the level of trypsin inhibitors. It's not exactly the same answer, but it gives you an indication whether this product has been heat treated properly. And then for soybean meal, the other one that you can do is solubility of the protein. If it is lower than 75%, then the product have been overheated, and there can be heat damage to the protein. And the last I would mention is that if you measure the lysine content, and the lysine content is less than 6% of the crude protein content, then there's a very big risk of heat damage and low digestibility. But this goes for soybean meals. They cannot directly be applied on the fermented or the enzyme treated or the soy concentrates, because they have undergone other processes and been affected in other ways.
All right, so I hope that answers your question, Liani. And I think we still have a few more time to get one question again. This one, the question is, can we replace the SBM with canola meal 100% in dairy? But we can found good results. Can you explain this?
Or can you repeat the last?
I think he's saying, but if we can find good results, how can you explain that? If we need to replace the SBM with canola meal 100% in dairy.
In dairy production, yeah. Yeah, of course, the fully developed ruminants have a much better ability to utilize rapeseed meal than monogastric animals. For pigs especially, and especially for young pigs, it's very difficult to handle the amount of crude fiber that comes along with the rapeseed meal. So you can only use a few percent before it starts affecting them. But for a ruminant with a functional rumen, the fibers is no problem. And rapeseed protein, when you look away from the fiber, is actually a very good protein source. And actually, I used to be a ruminant product manager in a feed mill, and it was only very rarely that we did use any soy at all in these diets. It is quite possible to make a very good dairy product with just based on sunflower and or rapeseed proteins. All
right. So I think we can just have one more questions before we finally end this session. The last question, Mr. Andersen, is which anti-nutrient is the most important, and you can further elaborate on it.
Yeah, well, it's a good question because it depends very much what is the issue. If the issue is poor feed conversion, it's most likely that the most important is the trypsin inhibitors blocking the protein from being digested and therefore not giving a very good feed conversion. But if the problem is coli diarrhea or lots of weaning diarrhea, then it's much more likely than the protein or the most important nutrient are the oligosaccharides and the sugars in the soya, because they're feeding the coli bacteria, making them grow more. And in that case, it can also be the antigenic protein destroying the surface of the small intestine and therefore causing diarrhea. So first diagnose what is wrong with the pigs, and then consider what are we putting in the feed. Is there something which can affect that? All right.
So I think that's it for the first session in our afternoon. Thank you so much, Mr. Lars Andersen, for your time today. And I do hope that everyone has learned so much in his topic. So if you want to get a copy of this presentation, kindly send us an email so we can send it to you, or you can email Hamlet for any further questions. Once again, thank you, Sir Lars Andersen.
Thank you very much.